The universe is a grand cosmic masterpiece, but what if I told you that most of its architects remain hidden from sight? Right now, forces we can't see, dark matter weaving through galaxies, quantum fields humming beneath empty space, are shaping everything around us. You walk through these invisible currents every day without even realizing it. Today, we're pulling back the curtain to reveal 30 of these mysterious phenomena, from the mind-bending power of black holes to the subtle tug of gravity's secrets. Buckle up, this journey will change how you see the cosmos. Picture this: galaxies spinning so fast that their stars should be flung into the void, yet something unseen holds them together. That cosmic glue, dark matter, it doesn't shine, reflect, or absorb light, making it completely invisible to our telescopes. But we know it's there because its gravitational grip bends the fabric of space itself. Back in the 1970s, astronomer Vera Rubin noticed something bizarre. Stars at the edges of galaxies moved just as fast as those near the center. According to the laws of physics, they should have slowed down unless an invisible force was anchoring them. That's when the hunt for dark matter began. Today, scientists estimate it makes up 27% of the universe, 5 times more than all visible matter combined. Experiments like LUX Zeppelin, buried deep underground to shield from interference, are searching for faint whispers of dark matter particles. Think of it as cosmic detective work, piecing together clues from the shadows of the universe. While dark matter pulls the universe together, its mysterious counterpart does something far stranger. Dark energy pushes everything apart. Back in 1998, astronomers made a jaw-dropping discovery while studying distant supernova. These dying stars weren't just moving away from us, they were speeding up as if some invisible hand were stretching space itself faster and faster. That's when scientists realized the cosmos isn't just expanding, it's accelerating, and the culprit, dark energy, a force so dominant it makes up 68% of the universe. Einstein actually predicted something like this a century ago with his cosmological constant, a mathematical placeholder for an unseen energy woven into space. He later called it his greatest blunder, but turns out he might have been onto something. Unlike gravity, which pulls, dark energy behaves like anti-gravity, creating a repulsive force that overwhelms everything else on cosmic scales. Picture blowing up a balloon with dots on its surface. As it inflates, each dot races away from the others. Now imagine the balloon starts expanding even faster on its own. That's our universe right now, with dark energy as the unseen breath driving it. The strangest part, we have no idea what dark energy actually is. Is it a property of space itself or something entirely new? Projects like the Dark Energy Survey are mapping millions of galaxies to trace its influence, while space telescopes peer deeper into the cosmic past for clues. One thing's certain, this enigmatic force is rewriting the fate of the cosmos, pushing galaxies apart until one day they'll vanish beyond the edge of sight. Even in the deepest voids of space, where nothing seems to exist, the universe is far from empty. Beneath the stillness, there's a seething chaos, particles and their mirror opposites, matter and antimatter, flickering in and out of existence so fast we can barely detect them. These are quantum vacuum fluctuations, ghostly bursts of energy that defy our everyday intuition. Think of space as a cosmic dance floor where pairs of particles appear, twirl for an instant, then vanish again before they can crash the party. This isn't just theoretical, we've seen its fingerprints in experiments like the Casimir effect. Place 2 metal plates incredibly close together in a vacuum, and suddenly they're tugged toward each other by an invisible force. Why? Because the quantum froth between them gets squeezed out, leaving less energy than the bustling activity outside. The plates are literally pushed together by the weight of nothingness. But the wildest consequence might be Hawking radiation, where black holes aren't completely black. At the edge of a black hole's grip, these virtual particles get torn apart. One falls in while the other escapes as real energy. Over eons, this slow leak causes even the mightiest black holes to evaporate. It's as if the universe has woven self-destruct mechanisms into its darkest monsters. So next time you look up at a quiet night sky, remember, what seems like empty space is anything but it's a turbulent quantum sea, shaping everything from the tiniest atoms to the fate of black holes. Less than a trillionth of a second after the Big Bang, something extraordinary happened. The entire universe expanded faster than the speed of light. Not just a gentle stretch, but an explosive growth spurt that doubled its size over and over again in fractions of a second. This is cosmic inflation, the universe's ultimate magic trick, turning a speck of space smaller than an atom into something approaching astronomical scales almost instantly. Why does this matter? Picture two distant regions of the universe that have identical temperatures but are too far apart for light to have traveled between them. Without inflation, this cosmic coincidence makes no sense. It's like walking into two bakeries on opposite sides of the planet and finding identical cookies still warm from the oven. Inflation solves this horizon problem by stretching a tiny, uniform patch of space so rapidly that all corners were once close enough to share the same conditions before being flung apart. The echoes of this violent expansion might still linger in the fabric of space-time as primordial gravitational waves, ripples that could tell us inflation really happened. Projects like the BICEP telescope at the South Pole scan the cosmic microwave background, the oldest light in the universe, searching for faint spiral patterns imprinted by these waves. It's detective work on a cosmic scale, hunting for wrinkles in time left over from the universe's first moments. And here's the mind-bending part: inflation didn't just happen once. Some theories suggest our universe might be one bubble in an endless froth of inflating regions, each with its own laws of physics, a multiverse where reality is more vast and varied than we could ever observe. Whether inflation was a one-time event or part of an eternal cycle, one thing's clear: the early universe played by rules that make our everyday physics look like child's play. Hidden beneath the visible glow of stars and galaxies, an invisible cosmic web of magnetism stretches across the universe, threading through galaxy clusters, bending the paths of particles, and possibly holding secrets from the dawn of time. These are primordial magnetic fields, enigmatic forces that may have been woven into the fabric of space itself moments after the Big Bang. Unlike the magnetic fields we know, like Earth's protective shield or the pull of a simple fridge magnet, these primordial fields operate on an unimaginable scale. Some span millions of light years, guiding cosmic rays and shaping the structure of entire galaxy clusters. But here's the puzzle: magnetic fields shouldn't last this long or grow this strong without a power source. Yet they persist, faint but undeniable, like ghostly imprints from the universe's infancy. So how do we detect something so subtle? Enter Faraday rotation, a cosmic sleight of light. When radio waves from distant quasars pass through magnetized regions of space, their polarization twists like a compass needle wobbling in an unseen current. By measuring this twist, astronomers map magnetic fields in places we'd never see otherwise. The results are staggering: delicate magnetic tendrils wrapping around galaxy filaments like invisible silk. Theories about their origins range from cosmic thunderstorms in the early universe, where turbulent plasma acted like a giant dynamo, to phase transitions in the primordial soup, where shifts in fundamental forces left behind magnetic fossils. Some even suggest these fields could have nudged the first galaxies into shape, a hidden hand guiding cosmic evolution. What's certain is this: magnetism isn't just a local phenomenon. It's written into the universe's blueprint, a whisper from a time before stars. And as telescopes grow more sensitive, we might finally decode whether these fields are relics of creation or clues to something even deeper. Of all the particles racing through the cosmos, none are as elusive as neutrinos, trillions of them streaming through your body every second without a trace. These ghostly particles barely interact with matter, slipping through planets like they're not even there. But here's where it gets weirder. Neutrinos have a secret identity crisis. They morph between three flavors: electron, muon, and tau. Mid-flight, a quantum shuffle called neutrino oscillation. This isn't just a quirky subatomic trait, it's a cosmic bombshell. For decades, scientists assumed neutrinos were massless like photons, but oscillations proved otherwise. Only particles with mass can switch identities this way. Suddenly, this phantom of the particle zoo had weight, upending the standard model of physics. Detecting them requires some ingenuity, like the Ice Cube Observatory at the South Pole, where thousands of sensors are buried deep in Antarctic ice. When a rare neutrino does collide with an atom, it creates a faint blue streak of light, revealing its origin. Some come from our sun, others from Earth's atmosphere, but the most thrilling are astrophysical neutrinos hurled across space by supernova or black hole jets. Speaking of supernova, these stellar explosions flood the cosmos with neutrinos. In fact, when a star collapses, 99% of its energy escapes as neutrinos, an invisible tsunami that outshines entire galaxies. During the famous supernova 1987A, detectors caught a handful of these particles hours before the light reached Earth, proving they're the universe's earliest disaster alarms. Now, scientists chase cosmic messengers from cataclysms like neutron star collisions, hoping to decode their oscillations for clues about dark matter, extra dimensions, or why the universe favors matter over antimatter. Neutrinos may be faint, but their whispers could rewrite physics. Somewhere in the vast darkness between galaxies, an invisible cosmic ballet is underway. Particles so light they barely register as matter, yet their collective dance might hold the key to two of physics' greatest mysteries. Meet the axion, a hypothetical particle so wispy that trillions could pass through you every second without a single collision. Yet together, they might form the elusive dark matter that binds the cosmos. The axion wasn't dreamed up just to explain missing mass. It emerged from an elegant solution to one of quantum physics' most puzzling gaps, the strong CP problem. Here's the conundrum. The equations governing the strong nuclear force which glues atomic nuclei together suggest something bizarre. Under certain conditions, neutrons should wobble in electric fields far more than they actually do. It's as if nature forgot to follow its own rules, leaving physicists scratching their heads for decades. Enter the axion, a theoretical particle proposed in the 1970s to restore cosmic balance. Picture it as a cosmic pacifier, subtly tweaking the equations until the math aligns with reality. But here's the twist: if axions exist, they'd also behave exactly like cold dark matter, barely interacting with ordinary matter except through gravity. A single axion would weigh billions of times less than an electron, yet collectively, their sheer numbers could form the hidden scaffolding of the universe. So how do you catch a particle that's practically a ghost? Teams like the axion dark matter experiment ADMX are turning to quantum ingenuity. Inside a powerful magnetic field, axions should occasionally convert into faint microwave photons. The experiment uses ultra-sensitive resonant cavities, tuned like cosmic radio receivers, to listen for these whispers. Imagine trying to hear a single raindrop in a thunderstorm. That's the precision required to spot an axion signal. But the hunt doesn't stop there. Some theories suggest axions might leave faint imprints in the polarization of starlight as it traverses magnetic fields in space, while others propose they could condense into bizarre, star-like objects called axion stars. Whether these particles are out there or not, one thing's certain: the quest for axions is forcing us to push technology to its limits, and in the process, we might just rewrite the rules of the universe. What if everything we think we know about gravity is incomplete? For decades, dark matter has been the leading explanation for why galaxies spin faster than expected, but there's another theory daring to rewrite the rules. It's called modified Newtonian dynamics, or MUND, and it suggests something radical. Maybe gravity itself behaves differently when its pull becomes incredibly weak. Proposed in the 1980s by physicist Mordechai Milgrom, MUND challenges a core assumption of Newton's laws. Instead of invoking invisible dark matter to explain galactic motions, Milgrom argued that our equations for gravity might simply break down at extremely low accelerations like those at the fringes of galaxies. Picture a car's gas pedal, press it lightly and the response is gentle, but below a certain threshold, the engine doesn't behave as predicted. MUND suggests gravity has a similar glitch in cosmic outskirts, subtly bending the rules rather than requiring unseen matter. At first glance, the math works startlingly well. MUND accurately predicts the rotation curves of many spiral galaxies without invoking dark matter, something even its critics admit is impressive. But here's where the theory hits turbulence. When we zoom out to galaxy clusters, colossal structures bound by gravity, MUND struggles to explain their observed motions without still needing some extra hidden mass. Worse, the Bullet Cluster, a cosmic collision where visible matter and gravitational effects visibly separate, appears to showcase dark matter directly, leaving MUND scrambling for alternate explanations. Yet the debate isn't settled. Some researchers argue MUND's underlying principle might point to a deeper truth, like an overlooked aspect of Einstein's relativity that only emerges on galactic scales. Others are exploring hybrid models where dark matter and modified gravity coexist in an uneasy truce. What makes this clash so fascinating isn't just the science, it's the reminder that even our most trusted laws might be approximations waiting for a revolutionary tweak. Whether MUND survives or falls, its boldness has already reshaped how we question the universe's hidden blueprints. Even as you sit perfectly still, our entire galaxy is racing through space at a staggering 14 million miles per hour, not away from something, but toward an invisible cosmic behemoth known as the Great Attractor. Hidden behind the dense stars and dust of our own Milky Way's disk, this gravitational mystery has been pulling thousands of galaxies in our cosmic neighborhood for billions of years. The challenge, it lies in what astronomers call the zone of avoidance, a region so obscured by our galaxy's own brightness that traditional telescopes can't peer through. It's like trying to spot a lighthouse through a blizzard, but thanks to infrared and radio wavelengths that pierce the cosmic fog, we've begun mapping this hidden realm. What we've found flips the script. The Great Attractor isn't alone. It's just one anchor point in an even larger structure, the Laniakea supercluster, a sprawling web of galaxies stretching over 500 million light-years. Here's the cosmic twist. Laniakea, which means immense heaven in Hawaiian, isn't just a random collection of galaxies. It's a river of motion, with everything inside it flowing toward the same gravitational valley like leaves caught in a slow-moving whirlpool. The Great Attractor sits near its core, but even it seems to be drifting toward something larger, the Shapley supercluster, a staggering concentration of mass 800 million light-years away. So what is the Great Attractor? Current theories suggest it's not a single massive object, but a dense knot of galaxy clusters, hundreds of thousands of galaxies clumped together, their combined gravity bending the paths of everything around them. Yet the sheer scale of this motion hints that we're still missing pieces of the puzzle. Each new observation peels back another layer, revealing a universe far more dynamic and interconnected than we ever imagined. One thing's certain, this hidden force sculpting our galactic journey reminds us that we're not just observers of the cosmos, we're passengers, swept along in a gravitational tide we're only beginning to understand. Even the most monstrous black holes have an expiration date thanks to a ghostly glow theorized by Stephen Hawking that slowly drains their energy. But this discovery came with a cosmic catch. Hawking radiation might be erasing information from the universe, shredding the very rules that quantum physics says should be unbreakable. This is the black hole information paradox, a battle between gravity and quantum mechanics where the stakes are nothing less than reality's instruction manual. Here's the problem. Quantum mechanics insists that information, the detailed state of every particle, can never be truly lost. Even if you burn a book, its ashes retain a subtle imprint of every word. But when matter falls into a black hole, it's supposedly crushed into a singularity, a point of infinite density where ordinary physics breaks down. If that black hole later evaporates via Hawking radiation, which appears random, where does the original information go? It's like tossing a library into a furnace and claiming the smoke carries no trace of the books. Physicists have scrambled for solutions. One controversial idea: firewalls, searing walls of energy just inside the event horizon that obliterate anything crossing them. Imagine a black hole's edge isn't smooth but lined with cosmic barbed wire, violently preserving information by destroying it early. Others propose the holographic principle, where all 3D information swallowed by a black hole is encoded on its 2D surface, like a cosmic DVD where the movie's entire plot is etched onto the label. Recent gravitational wave detections from black hole mergers might hold clues. When these titans collide, their final merged form briefly rings like a bell, and the tone of that ring could reveal whether information survives. Some theories suggest extra hairs on black holes' subtle imprints of what fell in alter these gravitational waves in detectable ways. The paradox forces us to ask, is our universe a meticulous archivist, or does it allow cosmic shredders? Solving this might require rewriting physics itself, a reminder that even the darkest corners of space refuse to let us take the rules for granted. What if the universe isn't as random as we think? Buried in the faint afterglow of the Big Bang, the cosmic microwave background, there's a peculiar pattern that's shaken cosmologists for decades. They call it the axis of evil. No, it's not a sci-fi plot twist, it's a bizarre alignment in the oldest light we can see, where temperature fluctuations in the CMB seem to sync up with the plane of our solar system. Here's why that's unsettling. The cosmic microwave background should be a cosmic fingerprint, random, isotropic, with no preferred direction. But when scientists mapped its largest scale patterns, the quadrupole and octupole moments, they found an eerie correlation with the ecliptic, the path Earth follows around the Sun. It's like discovering the spray-painted graffiti on the universe's oldest wall somehow spells out your home address. The implications are staggering. Could this mean our observations are contaminated by some unseen local effect? Or does it hint at something far stranger, a pre-Big Bang structure imprinted on reality itself? Skeptics argue it might just be observational noise or flaws in data processing. After all, peeling the universe's first light from the haze of galactic dust is like listening for a whisper in a hurricane. But for those who take it seriously, the axis of evil opens wild possibilities. Maybe the universe isn't perfectly uniform. What if it's lopsided, with a primordial tilt that's left a ghostly axis frozen into space-time? Some theorists even suggest this could be a scar from a collision with another universe in a multiverse foam, or evidence of an earlier cosmic phase that set the stage for our Big Bang. The Planck satellite's ultra-precise CMB maps haven't settled the debate, leaving room for both skepticism and speculation. Whether it's a measurement quirk or a cosmic clue, one thing's clear: if this axis is real, we might need to rewrite the opening chapter of the universe's story, one where the very fabric of reality has a hidden North Star. Imagine a clock that keeps perfect time forever, without batteries, without winding, without any energy at all. Sounds impossible, right? Welcome to the mind-bending world of time crystals, a phase of matter so strange it defies the most basic laws of physics we know. Unlike ordinary crystals, where atoms arrange themselves in repeating spatial patterns, time crystals tick through states in a repeating temporal loop. like a cosmic metronome that never winds down. The concept seemed like pure science fiction until 2017, when two teams, one at Harvard, another at the University of Maryland, used chains of trapped ions and diamond defects to bring these quantum curiosities to life. Here's the magic: when nudged by a laser pulse, the systems didn't settle into equilibrium like normal matter. Instead, they started oscillating at a fraction of the pulse's frequency, locking into a rhythm that couldn't be explained by classical physics. It's as if you tapped a pendulum once and it kept swinging forever, ignoring friction entirely. What makes time crystals so revolutionary? They're the first objects to break time translation symmetry, a fancy way of saying they behave differently at different points in time without energy input. Normally, that's forbidden by thermodynamics. You can't get infinite motion for free. But quantum entanglement twists the rules, allowing these systems to dance in perpetual harmony with themselves. The real excitement lies in their potential. Time crystals could revolutionize quantum computing by protecting fragile qubits from decoherence. Think of them as shock absorbers for information in a vibrating quantum hard drive. And because they resist thermal noise, they might unlock ultra-precise sensors or even new forms of cryptography. Of course, there are puzzles left. Do time crystals truly exist in nature, or are they lab-made miracles? Could they help us probe deeper mysteries like the nature of time itself? For now, these eerie quantum rhythms remind us that the universe still holds phenomena stranger than fiction, where time doesn't just pass but dances. For centuries, the laws of physics have been clear. To move forward, you need to push something backward. Rockets expel exhaust, jets push air. Every action has an equal and opposite reaction. But in the late 1990s, a British inventor named Roger Shawyer claimed to break this fundamental rule with a device no bigger than a microwave oven. The M drive, short for electromagnetic drive, promised thrust without propellant, a concept so revolutionary it could have rewritten space travel. The design was deceptively simple, a copper cone filled with microwaves bouncing back and forth. According to Shawyer, the shape of the chamber somehow created uneven radiation pressure, generating a tiny but measurable push toward the narrow end. No fuel, no exhaust, just pure, reactionless thrust. Skeptics immediately cried foul, pointing out this defied Newton's third law. Yet when NASA Eagleworks lab tested a prototype in 2016, they recorded an anomalous force. Suddenly, the impossible seemed plausible, but science thrives on scrutiny. Independent teams tried replicating the results, and the truth slowly unraveled. The thrust wasn't coming from some new physics, it was a thermal illusion. As the microwaves heated the chamber, metal expanded unevenly, creating minute shifts that mimicked thrust. Even Earth's magnetic field or vibrations from nearby electronics could skew measurements. By 2021, a meticulous study in Nature confirmed the verdict: the M drive was a mirage. The real lesson here isn't about failure. It's about how science self-corrects. For years, the M drive captivated imaginations, from basement inventors to aerospace engineers. It challenged dogma, spurred innovation in measurement techniques, and reminded us why skepticism is just as vital as discovery. While the dream of propellantless thrust fizzled, the pursuit of revolutionary ideas never will. After all, today's impossible often becomes tomorrow's breakthrough, just not always the way we expect. The cosmos is expanding, we've known that for nearly a century. But here's the hitch: depending on how you measure it, the universe seems to be growing at two different speeds. This headache for cosmologists is called the Hubble tension, and it's forcing us to question whether we've missed a fundamental piece of the cosmic puzzle. On one side, we have precise measurements of nearby stars and supernovae, what astronomers call the local universe. These observations peg the expansion rate, known as the Hubble constant, at around 73 kilometers per second per megaparsec. That means for every 3.3 million light-years you look outward, galaxies appear to race away 73 kilometers faster each second. But when we peer back to the universe's infancy using relics like the cosmic microwave background, the math tells a different story. According to these ancient snapshots, the Hubble constant should be closer to 67, a glaring 9% slower than what we see nearby. It's as if the universe started with one speed limit and quietly changed the rules halfway through. So what's causing this cosmic speed mismatch? One leading suspect is early dark energy, a mysterious extra dose of repulsive force that might have briefly surged during the universe's first few 100,000 years, tweaking its expansion before fading away. Think of it like a hidden booster rocket that gave the cosmos an extra nudge before we started measuring. Other theories suggest more radical fixes. Perhaps gravity itself behaves differently over cosmic distances, or our understanding of dark matter needs an overhaul. The stakes couldn't be higher. If the discrepancy is real, not just a measurement fluke, it could mean there's an unseen ingredient or force altering the universe's evolution. Telescopes like the James Webb Space Telescope are now double-checking local measurements, while next-generation observatories aim to settle the debate with even finer precision. Whatever the answer, the Hubble tension is a reminder that the universe still holds surprises, and sometimes the most basic questions, like how fast is space growing, can lead us straight to the edge of known physics. While the Great Attractor pulls us toward its hidden mass, there's another cosmic force working in opposition, an immense void so empty it's actively pushing us away. Meet the dipole repeller, a vast desert of space stretching over hundreds of millions of light years, where galaxies are eerily scarce and gravity's grip is weakened by absence. Here's how it works. Imagine space as a cosmic trampoline where clusters of galaxies create deep dents that pull matter inward. But in a void like the dipole repeller, the trampoline isn't just flat. It's slightly raised, creating a gentle hill that nudges galaxies outward. This isn't some mysterious anti-gravity. It's the universe's way of balancing the scales. With so little mass concentrated here, the expansion of space dominates, effectively repelling nearby structures. Maps of galaxy flows reveal this tug-of-war clearly. Our local group, the Milky Way and its neighbors, is caught between two giants, the Great Attractor's pull and the dipole repeller's push. But the story gets even stranger. Some astronomers argue this motion might be part of a larger, dark flow, where entire clusters of galaxies are drifting in the same direction, as if tugged by something beyond the observable universe. Could there be an unseen structure so massive its gravity leaks into our cosmic horizon? The dipole repeller challenges our assumptions about emptiness. Far from being passive gaps, cosmic voids might actively shape the paths of galaxies, sculpting the large-scale structure of the universe. As telescopes peer deeper into these deserted regions, they're uncovering a dynamic cosmos where even nothingness plays a starring role, a reminder that sometimes the absence of something can be just as powerful as its presence. Here's the next mystery that defies all intuition: particles that remain mysteriously linked across unimaginable distances, as if the universe itself forgets to keep them apart. This is quantum entanglement, a phenomenon so bizarre Einstein famously dismissed it as spooky action at a distance. Yet decades of experiments have proven him wrong. The universe doesn't just allow this connection, it thrives on it. Take the Bell test experiments, where particles are created in pairs with intertwined properties. Even when separated by thousands of miles, measuring one instantly determines the state of its partner, as though space and time don't apply to their relationship. It's not telepathy, it's something deeper. The particles aren't sending signals, they exist in a shared reality where their fates are sealed before we even look. But the real frontier lies where entanglement collides with gravity's grip. Black holes, the universe's ultimate information shredders, might be entangled with the particles they've swallowed. Theorists like Leonard Susskind propose E equals EPA, a radical idea where wormholes, Einstein-Rosen bridges, could physically manifest quantum entanglement, stitching space together with threads we can't see. Picture two black holes born from the same star collapse. Their interiors might be connected by a hidden tunnel, making entanglement a feature of spacetime itself. Recent breakthroughs in quantum gravity are testing these wild proposals. Laboratories are now entangling microscopic drums, weighing heavier objects to see if gravity plays by quantum rules. If entanglement can survive in these extreme regimes, we might finally crack the code unifying quantum mechanics and gravity, a theory of everything. So next time you hear about spooky action, remember, it's not magic. It's the universe whispering that our ideas of separation and distance might just be illusions, and that the fabric of reality is far stranger and more connected than we ever dreamed. High above Earth, lost in the endless chatter of orbiting satellites, there's one object that has fueled decades of speculation, a shadowy silhouette dubbed the Black Knight. Some claim it's an alien probe parked in polar orbit for 13,000 years, silently watching us. Others insist it's just space junk, a mundane piece of human debris caught in the cosmic currents. So where does myth end and reality begin? The legend took flight in the 1950s when newspapers reported mysterious radio signals allegedly coming from an unknown satellite years before Sputnik. By the 90s, grainy images from NASA missions showed a dark, irregular shape against Earth's crescent, igniting theories of an extraterrestrial artifact. The most persistent claim that this object predates human spaceflight entirely, its orbit defying natural explanation. But let's rewind the tape. In 1998, astronauts on the ISS spotted something unusual during a spacewalk, a lost thermal blanket drifting away after an equipment mishap. The size, the shape, even the way it tumbled matched descriptions of the so-called Black Knight. Space agencies have documented countless cases of debris like this: discarded insulation, spent rocket stages, even a glove floated away in 1965. The truth is, Earth's orbit is cluttered with remnants of our own exploration, each piece reflecting sunlight in eerie, unpredictable ways, yet the mystery lingers for a reason. The Black Knight taps into something deeper: our fascination with the idea that we're not alone, and that evidence might be hiding in plain sight. While scientists track over 27,000 catalogued objects circling our planet, the line between fact and folklore blurs when sunlight hits a stray bolt just right. Perhaps the real lesson here isn't about alien visitors, but about how easily the vast unknown of space can become a mirror for our imagination. After all, in the silence between stars, we're always listening for echoes, whether they come from ancient probes or our own forgotten hardware. On a quiet Ohio night in 1977, a radio telescope captured a signal so extraordinary that the astronomer who found it circled the printout and wrote one word in red ink: wow. For 72 seconds, a burst of narrowband radio waves, exactly the frequency scientists predicted alien civilizations might use, blared from the constellation Sagittarius before vanishing without a trace. Decades later, that fleeting blip remains the most tantalizing candidate for extraterrestrial contact in history. Recent efforts like Breakthrough Listen have brought fresh scrutiny to this cosmic mystery. Using state-of-the-art telescopes, they've scanned the same patch of sky, hunting for repeats of the signal. But silence lingers: no follow-up bursts, no patterns, just that eerie one-time ping. Some researchers now suggest a more mundane culprit: comets. Back in 2017, a study proposed that two icy wanderers passing through the inner solar system that year, previously undocumented in 1977, could have emitted hydrogen clouds that reflected sunlight, mimicking the WOW signal's frequency. Yet doubts linger. The signal's intensity and narrow bandwidth still don't perfectly match known comet behavior, and no comets were catalogued in Sagittarius's direction that summer. Alternative theories range from a rogue satellite reflection to an exotic astrophysical flare, but none fully explain why the signal hasn't recurred. What makes the WOW signal endure isn't just the science, It's the reminder that amid the cosmic noise, there are still moments that jolt us with possibility. Whether it was a passing comet or something far more profound, that 72-second whisper challenges us to keep listening, because the next signal might not just say, "Wow." It might say, "Hello." The universe is unimaginably vast, with trillions of galaxies, each hosting billions of stars and planets. Statistically, life beyond Earth should be everywhere. So where is everybody? This is the Fermi paradox, a haunting contradiction between the high probability of extraterrestrial civilizations and the eerie silence we've found so far. One chilling explanation: the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. It might lurk in our past, meaning the leap from simple chemistry to complex life is astronomically rare. Or worse, it could lie ahead, a self-destructive trap like nuclear war, climate collapse, or runaway AI that wipes out civilizations before they reach the stars. Others propose less dire answers. The zoo hypothesis suggests advanced species observe us from a distance, like interstellar anthropologists preserving Earth as a cosmic nature reserve. Or perhaps we're simply looking for the wrong signs. Alien technology might operate on principles so foreign we wouldn't recognize it. That's where projects like JWST come in. Instead of listening for radio signals, astronomers now hunt for technosignatures, industrial pollutants in exoplanet atmospheres, city lights on distant worlds, or even massive alien megastructures like Dyson spheres that harness a star's energy. Early targets include KIC 8462852, a star with bizarre, irregular dimming that some speculate could be artificial. Yet after decades of searching, the silence holds. Maybe we're early to the cosmic party, or latecomers to an interstellar conversation happening on wavelengths we haven't tuned into. Or perhaps the answer is simpler. In a universe this vast, distances and time might conspire to keep civilizations forever isolated. The paradox isn't just about aliens, it's a mirror forcing us to confront how fragile or how alone we might truly be. Out beyond Neptune's orbit, where sunlight fades to a dim glow, astronomers have stumbled upon a cosmic cliffhanger, quite literally. The Kuiper Belt, a sprawling ring of icy debris left over from the solar system's birth, doesn't gradually thin out as expected. Instead, it drops off sharply around 50 astronomical units from the Sun, a boundary so abrupt scientists call it the Kuiper Cliff. It's as if someone drew a line in the cosmic sand and said, "No further." This sudden cutoff defies everything we know about how planetary systems form. Normally, debris disks like the Kuiper Belt should fade smoothly with distance, like ripples dissipating in a pond. Yet when telescopes like Subaru and Pan-STARRS mapped this region, they found a dramatic scarcity of objects beyond 50O, a missing population that shouldn't exist. So what's carving this invisible edge? One tantalizing idea involves Planet 9, a hypothetical world up to 10 times Earth's mass lurking hundreds of O away. Its gravity could have shepherded distant Kuiper Belt objects into odd orbits while clearing out the neighborhood beyond 50O, like a cosmic broom sweeping debris into piles. Computer simulations show this might work, but there's a catch. After years of searching, Planet 9 remains elusive. Alternative theories are just as intriguing. Maybe the cliff marks where the young sun's protoplanetary disk simply ran out of material, like a factory conveyor belt stopping mid-production. Or perhaps a passing star grazing our solar system billions of years ago stripped away the outer Kuiper Belt like a thief in the night. Some researchers even suggest primordial black holes, tiny, ancient relics of the Big Bang, could be lurking out there, their gravity sculpting the cliff we see today. The hunt for answers is pushing telescopes to their limits. Every new survey of the Kuiper Belt brings us closer to understanding whether this boundary is a signpost of unseen planets, a fossilized record of our solar system's violent youth, or something even stranger. One thing's certain, the Kuiper Cliff isn't just a curiosity, it's a gateway to the solar system's best-kept secrets. In October 2017, astronomers spotted something that shattered all expectations. A strange, tumbling object racing past our sun at nearly 200,000 miles per hour. Unlike anything in our solar system, its trajectory revealed an impossible truth. This visitor came from beyond our stars. Named Oumuamua Hawaiian for Scout, it became the first known interstellar traveler. But long after it vanished into the void, one detail kept scientists up at night: the way it moved. As Oumuamua sped away, something peculiar happened. Instead of slowing down under gravity alone, it accelerated just slightly, but enough to defy conventional explanations. Normally, comets show this kind of push when sunlight vaporizes their ices, creating a jet of gas that acts like a thruster. Yet Oumuamua left no visible tail, no dusty halo. So what gave it that extra kick? Some researchers pointed to hidden outgassing, perhaps subsurface pockets of hydrogen or nitrogen erupting invisibly as the sun warmed its surface. Others proposed an even wilder idea. What if Oumuamua wasn't a natural object at all? Harvard astrophysicist Avi Loeb famously suggested it could be artificial, a fragment of alien technology, like a discarded light sail propelled by starlight's pressure. The math kinda fits. A thin, flat object tumbling through space would reflect sunlight in ways that match Oumuamua's odd brightness fluctuations. But extraordinary claims require extraordinary evidence, and skeptics weren't convinced. The lack of radio signals or visible debris dampened hopes of an alien artifact. Meanwhile, new studies suggest that Oumuamua's acceleration might be explained by exotic ices we've never seen up close: frozen hydrogen or nitrogen that vaporizes too subtly for our telescopes to catch. Whether it was a cosmic iceberg or something far stranger, Oumuamua left us with more questions than answers. Its fleeting visit reminds us that the universe is full of surprises, and that sometimes the most profound discoveries come in packages too mysterious to unpack. Future telescopes like the Vera Rubin Observatory might spot more of these interstellar nomads, finally revealing whether Oumuamua was a cosmic fluke or a glimpse of something far more extraordinary. Galaxies don't just drift apart in the cosmic expansion. Some are being pulled by something we can't see. Not dark matter, not dark energy, but a force so vast it might originate beyond the edge of our observable universe. Welcome to the dark flow, a mysterious river of galaxy clusters all streaming in the same direction at breakneck speeds. It started with data from NAS, a Wilkinson microwave anisotropy probe WMAP, which mapped the cosmic microwave background with unprecedented precision. Scientists noticed something off. Hundreds of galaxy clusters weren't just expanding with the universe, they were racing toward a specific patch of sky at nearly 2 million miles per hour. The kicker: there's nothing massive enough in that direction to explain the motion, at least nothing we can detect. Skeptics argue it could be a measurement error or an oddity in how we interpret cosmic radiation. But follow-up studies with the Planck satellite found the same eerie motion, suggesting it's real and enormous. So what's tugging these galaxies? One radical idea points to gravitational leakage from a neighboring universe, a cosmic next-door neighbor so massive, its gravity spills into ours like water seeping through a shared wall. Others propose it's a superstructure of dark matter so colossal, it warps the fabric of space on scales we've never mapped. Imagine a mountain range so vast you can only see its shadow, but that shadow stretches across billions of light years. Whether it's a statistical ghost or our first glimpse of the multiverse, the dark flow forces us to ask, is the cosmos we see just a tiny island in an ocean of unseen realities? Every new observation brings us closer to the answer or deeper into the mystery. Deep in the cosmic microwave background, there's a place where the afterglow of the Big Bang grows strangely dim, a vast, icy desert in the constellation Eridanus stretching over 1 billion light years. Astronomers call it the Eridanus supervoid, And it's not just empty, it's colder than the surrounding universe by a fraction of a degree, as if someone left a cosmic freezer door open in the fabric of space. At first glance, this cold spot might seem like a statistical fluke, a random fluctuation in the universe's baby picture, but the numbers don't add up. The odds of such an extreme void forming naturally are about 1 in 50,000, turning this into a full-blown cosmic whodunit. One theory: this isn't just emptiness, it's a bruise. A collision with another universe. The idea sounds like sci-fi, but some models of inflation suggest our universe might be one bubble in a frothing multiverse ocean. If a neighboring bubble universe grazed ours in the distant past, the energy released could have left a scar, a region where space stretched differently, leaving behind this eerie cold spot. Think of it like two soap bubbles bumping in mid-air. Where they touch, the surface warps in ways that linger long after. Skeptics aren't convinced. Alternative explanations range from a titanic cluster of galaxies distorting the CMB's light like a funhouse mirror, to undiscovered physics tweaking the early universe's expansion. The Planck satellite's data added fuel to the debate while it confirmed the cold spot's existence. It couldn't definitively rule out simpler causes. The truth might lie in the void itself. Upcoming galaxy surveys could reveal whether the Eridanus supervoid truly lacks matter on an unprecedented scale, or if something far stranger is casting this cosmic shadow. Whether it's proof of parallel universes or just a once-in-a-lifetime statistical oddity, one thing's clear: the universe still holds pockets of mystery so vast they make our textbooks feel like rough drafts. In the vast emptiness between planets where spacecraft glide silently for decades, sometimes the universe throws us a curveball, one so small that it took scientists years to notice. That's exactly what happened with the Pioneer anomaly, a tiny but persistent mystery that puzzled NASA for over 2 decades. When the Pioneer 10 and 11 probes launched in the 1970s, their mission was to explore the outer solar system before venturing into interstellar space. But as they traveled farther from the Sun, engineers tracking their trajectories noticed something bizarre. Both spacecraft were slowing down ever so slightly, just enough to defy predictions, as if an invisible hand were gently tapping the brakes. Over time, this discrepancy added up, leaving Pioneer 10 nearly 240,000 miles off course by the time it reached the edge of the solar system. At first, theories ranged from the exotic to the downright wild. Maybe dark matter was exerting an unseen drag, or perhaps our models of gravity itself were flawed at cosmic distances. Some even speculated about unknown planetary masses lurking beyond Pluto, but the truth turned out to be far simpler and far more humbling. After years of detective work, a team at NASA, a jet propulsion laboratory, cracked the case: heat. Not from some external force, but from the probe's own radioisotope power sources. Here's the catch: as the plutonium inside the Pioneer probes decayed, it emitted heat, and that warmth radiated unevenly off the spacecraft surfaces. Most of the energy escaped harmlessly, but a small fraction bounced off the back of Pioneer's dish-shaped antenna, creating a faint but steady push backward. Imagine blowing on a toy sailboat just hard enough to nudge it. That's thermal radiation pressure at work. It was a force so subtle it had been overlooked for years, buried in the noise of other calculations. The Pioneer anomaly taught scientists a crucial lesson. Sometimes the universe's greatest mysteries aren't grand cosmic secrets, but the quiet quirks of engineering. Today, missions like New Horizons account for this thermal effect from the start, ensuring their paths stay true. Yet the story lingers as a reminder: even in the age of precision spaceflight, the cosmos still finds ways to surprise us with the smallest details. Most galaxies are ruled by dark matter, its invisible grip holding stars in place against the whirl of cosmic motion. But in 2018, astronomers stumbled upon a cosmic rebel, NGC 1052 DF2, a ghostly galaxy that defies the rules by appearing to have no dark matter at all. This ultra-diffuse galaxy, a faint, wispy collection of stars, should have been torn apart by its own rotation without dark matter's anchoring pull. Yet there it was, cruising through space with its stars moving languidly, as if gravity itself had taken a day off. The discovery sent shockwaves through astrophysics, because if dark matter isn't universal, our models of galaxy formation might need a major rewrite. Skeptics scrambled for answers. Could tidal stripping, the gravitational equivalent of a cosmic mugging, have ripped away NGC 1052DF2's dark matter? Nearby galaxies might have stolen it billions of years ago, leaving behind a skeleton of visible stars. Others questioned the measurements themselves. Perhaps the galaxy's distance was miscalculated, skewing calculations of its mass. But here's the twist. Subsequent studies found more dark matter-free galaxies, deepening the mystery. Some researchers now propose these oddballs formed differently, perhaps in ancient collisions where gas was compressed into stars without the usual dark matter scaffolding. Others wonder if dark matter behaves in ways we haven't yet imagined, clustering unevenly across the cosmos like an invisible patchwork quilt. Whether NGC 1052DF2 is a statistical fluke or a signpost to new physics, one thing's certain: it's proof that the universe still has rule breakers lurking in the shadows, and they might just hold the keys to unlocking dark matter's ultimate secrets. Here's the vacuum of space, utterly empty, right? Not quite. According to quantum physics, even the void itself crackles with energy, a seething sea of virtual particles flickering in and out of existence. But here's where things get truly bizarre. An observer cruising at a constant speed sees nothing unusual, while someone accelerating suddenly finds themselves bathed in a warm glow of real particles. This is the unravel effect, a mind-bending prediction that turns our understanding of reality on its head. Named after physicist Bill Unravel, who proposed it in 1976, the effect reveals an unsettling truth. What you perceive as empty depends entirely on how you're moving. Imagine floating weightless in space one moment, then firing your rocket engines. As you accelerate, your sensors would pick up a faint thermal radiation particles that weren't there before, popping into existence just for you. To someone watching from a distance, though, the vacuum remains empty. It's as if motion itself warps reality, creating particles from pure acceleration. The math behind this echoes Hawking radiation, the eerie glow that leaks from black holes. Both phenomena hinge on the same quantum quirk, pairs of virtual particles separating near a horizon, whether it's the edge of a black hole or the acceleration-induced boundary an observer creates. In fact, some theorists argue the unravel effect is Hawking radiation viewed from a different perspective, two sides of the same cosmic coin. To test these wild ideas, scientists have built analog black holes in labs. Superfluid helium chilled near absolute zero can mimic spacetime's behavior, with sound waves playing the role of light trapped by gravity. When researchers accelerate the fluid, they've detected phonon pairs quantum ripples that mirror Unravel's predicted particles. It's not quite a smoking gun, but these experiments hint that the universe has a deeper layer of relativity we're only beginning to glimpse. What does it all mean? If the unravel effect is real, it suggests that particles, the very building blocks of matter, aren't just out there. They're performances in a quantum theater, appearing or vanishing based on the audience's motion. It's a humbling reminder that the cosmos doesn't play favorites. Even something as fundamental as existence depends on where you're standing and how fast you're going. For the first time in history, humanity stared directly into the abyss, and the abyss stared back. In April 2019, the Event Horizon Telescope collaboration unveiled an image that shattered expectations, a fiery ring of light encircling the pitch-black silhouette of M87 star, a supermassive black hole 55 million light-years away. This wasn't an artist's rendering or a computer simulation. it was a photograph of space-time itself bending under gravity's extreme grip. What makes this glowing halo so revolutionary? That ring isn't just hot gas, it's light from the accretion disk making a desperate escape. As photons skirt the edge of the black hole's event horizon, some get captured forever, while others are bent into our line of sight like a cosmic mirage. The darker center, that's the black hole's shadow, an area 2.5 times larger than the event horizon where even light's twisted paths inevitably spiral inward. It's the point of no return, etched against the universe's brightest backdrop. The image confirmed Einstein's predictions with stunning precision, but it also held surprises. The ring's uneven brightness hinted at wild turbulence in the disk, like a whirlpool with chaotic currents, and the shadow's shape, perfectly circular, proving M87 star spins relatively slowly, a clue about how this 6.5 billion solar mass monster grew over eons. Now, the EHT has set its sights on a new target, Sagittarius, a star, the supermassive black hole at our galaxy's heart. While it's 2,000 times closer than M87 star, it's also far smaller and more restless, with gas swirling around it at relativistic speeds in mere minutes rather than days. Capturing its portrait is like trying to photograph a toddler on a sugar rush compared to M87 star's stoic giant. Early teasers of the data suggest unexpected flares and potentially an even more distorted shadow, shaped by extreme frame dragging as spacetime itself gets yanked around the black hole's spin. These images aren't just pretty pictures, they're stress tests for gravity itself. Every flicker in that ring, every warp in the shadow could hint at physics beyond Einstein, or confirm once and for all that even in the universe's most extreme environments, relativity holds the pen that writes the rules. Take a step back, way back, until every galaxy you've ever seen shrinks into a single dot of light. Suddenly, a breathtaking pattern emerges. The cosmos isn't just a random scatter of stars. It's woven into a vast, intricate tapestry, a network of glowing filaments connecting galaxies like beads on invisible strings. This is the cosmic web, the hidden architecture of the universe, and its blueprint was written by dark matter billions of years ago. Simulations reveal its ghostly skeleton, dark matter threads stretching across unimaginable distances, forming highways where galaxies cluster at the intersections. But until recently, mapping this structure in the real universe seemed impossible. Enter DESI, the Dark Energy Spectroscopic Instrument, a revolutionary project that's building the most detailed 3D map of the cosmos ever made. Its secret weapon, baryon acoustic oscillations, faint ripples frozen into space from the universe's infancy. These ripples are cosmic mile markers. When the young universe was a seething plasma soup, sound waves raced through it, leaving behind spherical density patterns like echoes in a cave. As space expanded, these imprints stretched, locking galaxies into place along web-like filaments at roughly 500 million light-year intervals. DESI precision optics measure millions of galaxy positions, tracing these echoes to reconstruct the web's spine in 3 dimensions. What's astonishing is how closely reality matches theory. The filaments aren't just abstract lines, they're rivers of gas feeding galaxies, while the voids between them stretch for hundreds of millions of light years, nearly empty except for rogue stars flung out in cosmic collisions. Some filaments even glow faintly with the ultraviolet light of colliding hydrogen atoms, revealing where the web's strands ignite new stars, yet mysteries linger. Why do some regions of the web seem underpopulated compared to simulations? Could there be unknown forces sculpting these threads? With every new slice of its map, DESI brings us closer to answers, and to seeing the universe not as a chaos of points, but as a grand, woven design where even the emptiest voids play their part in the cosmic story. Imagine for a moment that you're the only conscious being in existence, not just on Earth, but in the entire universe. And what's more unsettling, you didn't evolve, you weren't born, you simply assembled out of the void by pure chance. This isn't the plot of a sci-fi story. It's a real thought experiment that keeps physicists up at night, known as the Boltzmann brain. The idea comes from Ludwig Boltzmann, the 19th century physicist who helped unravel the mysteries of entropy. He realized that given enough time, even the most improbable events will happen, including the spontaneous formation of a fully formed, self-aware mind in the chaos of empty space. Think of it like shuffling a deck of cards forever. Eventually, you'll get a perfect sequence by sheer luck. In an infinite universe, random fluctuations could, in theory, piece together neurons, memories, even an entire false reality, complete with the sensation of reading these words right now. Here's where it gets weirder. According to thermodynamics, a universe tending toward maximum entropy disorder should make complex structures like brains less likely over time. Yet if the cosmos is eternal, there's no reason why brief, low-entropy pockets couldn't flicker into existence, creating observers who believe they're in an ordered cosmos. Statistically, these random, isolated minds should outnumber beings like us who evolved in a structured universe. So why does reality seem so stable? Critics argue the Boltzmann brain paradox reveals a flaw in our assumptions. Maybe the universe isn't infinite, or perhaps there's an undiscovered law preventing such aberrations. Others suggest it's evidence we're missing a crucial piece of cosmology, like a definitive explanation for the arrow of time. After all, if time can flow backward in quantum experiments, why shouldn't consciousness emerge from the void? The takeaway isn't to doubt your own existence. It's a reminder that the universe's deepest mysteries often lurk at the intersection of physics and philosophy. Whether Boltzmann brains are a quirk of math or a profound clue about reality's scaffolding, they challenge us to ask, in a cosmos governed by chance, how do we know what's truly real? What if everything around us, the stars, the laws of physics, even the device you're watching this on, isn't real? Not in the way we think, anyway. This is the simulation hypothesis, the radical idea that our entire universe might be an artificial construct, an ultra-advanced computer program created by an unfathomable civilization. Philosopher Nick Bostrom laid out a startling trilemma. Either virtually all civilizations go extinct before reaching technological maturity, or they lose interest in creating simulations of their ancestors, or, and here's the kicker, we're almost certainly living in one of those simulations right now. The logic is unsettlingly simple. If future civilizations develop the power to simulate conscious beings, they could run countless iterations of their own history. And statistically, the odds of this being the original universe shrink to nearly zero. Some tech billionaires have even funded research to test this idea, scouring the cosmos for potential glitches, tiny imperfections in the fabric of reality that might reveal underlying code. Think of it like spotting pixels in a video game or catching physics errors where gravity stutters for a split second, but quantum mechanics throws a wrench in the theory. The universe at its smallest scales behaves probabilistically, with particles existing in superpositions until observed. That's a phenomenally inefficient way to program a simulation. Why calculate every possible state if you're just rendering a single outcome? Unless, of course, the randomness itself is a feature, a way to conserve processing power by only resolving realities when they're observed. Supporters point to eerily mathematical constants like the fine structure ratio, a number so precise it seems dialed in by hand. Detractors argue that invoking a simulator explains nothing, it just pushes the mystery up a level. After all, who created their universe? Whether we're code or cosmic accidents, the simulation debate forces us to confront a humbling thought. Reality might be far stranger than we're equipped to imagine. And until we find that glitch or prove it doesn't exist, the question lingers like an unsaved file, waiting to crash or confirm everything we think we know. From the ghostly pull of dark matter to the phantom glow of Hawking radiation, we've journeyed through 30 cosmic enigmas that keep scientists staring at the ceiling at night. These aren't just quirks of the universe, they are fundamental mysteries rewriting the rules of reality itself. Whether it's the eerie alignment of the axis of evil or the fleeting whispers of neutrinos, each force reminds us how much we don't yet understand about the grand tapestry of existence. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And he was right. Every strange signal, every unexplained motion, every shadow in the cosmic background is a clue waiting to be deciphered. Maybe you'll be the one to crack the next great mystery, or maybe we'll uncover it together. So tell me in the comments, which of these 30 forces blew your mind the most? Was it the quantum tango of entangled particles or the cosmic repeller pushing galaxies apart? Let's keep the conversation going. And if you're hungry for more space secrets, hit subscribe, because the universe never runs out of surprises. Until next time, keep looking up. The cosmos isn't done revealing itself just yet.